Welcome to the Tech Study channel. In the previous class, we have discussed about construction and working of a MOSFET, uh, which is about N-channel D-MOSFET. So, in this class, so we have completed all the transistors, means transistor, and then BJT and FET and JFET and MOSFET and DMOSFET and EMOSFET. Uh, their construction and working, and also how they act as a switch and amplifier. So in this ninth video we will discuss about 11th question and its answer. So 11th question is difference of JFET and MOSFET. So first we will discuss about transistor. What is transistor? Then FET. Then just we overview the working of all types of FETs, and then differences between MOSFET and JFET. So what is transistor? Transistor is a transistor is a fundamental semiconductor device used to switch or amplify electronic signals and power. So switching means switching on or off, and amplifying means increasing the strength of the signal. And transistors are categorized by whether they are controlled by input current or input voltage. If they are controlled by input current, they are called current control device. Example, BJT is bipolar junction transistor. And if they are controlled by input voltage, then they are called voltage control devices. FET, example, field effect transistor. So next we will see what is FET. FET is a field effect transistor is a voltage controlled three terminal semiconductor device used for switching or amplification. One type of FET is JFET, okay, and another type of FET is MOSFET. So in this video so what is so we will discuss working of the all types of FETs except BJT. BJT is not a FET, sorry. FET, all types of FET means JFET and MOSFET. And MOSFET is also of two types, D MOSFET and E MOSFET. So first we will see what is JFET. Okay. So JFET. JFET is a field effect transistor, is a three-terminal semiconductor device in which current conduction is by one type of carrier, electron or hole. Here is the three-terminal drain, source and gate, and is by one type of carrier, means electron or hole. If the JFET is N-channel JFET, then it is by electrons, conduction is by electron. And if it is P-channel JFET, then conduction is by P-type, means holes, okay. And then in the working of JFET, so here is the JFET. Gate is reverse biased. It is reverse biased, means negative terminal is connected to the P-type material and positive terminal is connected to the N-type material, okay. Here gate is of P-type material and drain and source are N-type materials, okay, which are connected to N-type bar. So the two PN junctions act at sides form two depletion layers. So here they are forming two depletion layers because of this reverse bias voltage, okay. The current conduction P is by the charge carrier. In this case, free electrons is through conducting channel between two depletion layer out of the drain. So here is the current conduction between two PN regions, okay, is out of the drain, okay. So current is from drain to source, and electron flow is from source to drain, okay. And the width and hence resistance of a conducting channel is controlled by input voltage VGS. This VGS, if we increase VGS, then this depletion layer will be increased, and the conducting channel will be decreased, and hence high resistance will be there, and the current from drain to source is decreased. Reverse will happen if VGS decreases, means the depletion layers will be thin, and the conducting channel size is more, means between area between two P types materials, okay. And means the magnitude for drain current ID is changeable by altering VGS, okay. We have understand working of JFET, then we'll understand working of MOSFET. So MOSFET, yeah, so it is there here. Gate is of metal or polysilicon. Here MOSFET diagram is there, N channel MOSFET. Gate is of polysilicon or metal, okay. And it is heavily doped because to provide high conductivity, perfect conductor by functioning effectively to quickly transmit voltage signals. Heavily doping increases the carrier concentration, making the material conductive. So, and then heavily doped because to narrow the depletion width when metal wire. Here is the metal wire, okay. Metal wire meets a semiconductor, means gate, and a potential current naturally forms. By heavily doping the gate material, the depletion region at this interface becomes extremely thin. So gate is heavily doped. So the depletion region between this metal and wire becomes extremely thin because the doping concentration is inversely proportional to the depletion region width, okay. And then this is the diagram of N channel MOSFET. Here is the source, gate and drain. Two N channels are there and P substrate is there, okay. And then because the silicon dioxide layer is an insulator, it prevents electrons from moving physically from the gate into the substrate, leading to very high input impedance. Here is the silicon dioxide which prevents the electrons moving from gate to P substrate. This whole area is P substrate, okay. And since charge can't flow through the oxide, a positive voltage applied to the gate causes a positive charge to build up on the gate side of the capacitor. Here is it produces positive charge. because we have applied a positive voltage, because silicon dioxide is preventing the electrons to flow from gate to p substrate, okay, to form a conducting channel. Initially we don't have a channel in the MOSFET, as we already know, and so we are trying to create the channel between two n plus regions. So then a positive voltage is applied now. So positive charge is built up on the gate, and negative voltage applied to the substrate, okay. And so the positive charge built upon the gate creates an electric field that generates through the oxide into the substrate. So this positive charge creates an electric field that creates an electric field that penetrates into the silicon dioxide and enters the substrate, okay. And then this field performs two tasks. It repels the majority carriers away from the surface. Majority carriers is what? Holes. It repels the holes at the area just beneath this silicon dioxide, okay. And it attracts minority carriers electrons from the bulk of the p substrate towards the oxide interface layer just beneath the silicon dioxide, and it also attracts electrons from n plus regions, uh, and it attracts n plus region electrons and plus p substrate minority carriers uh, towards this area that is just beneath the silicon dioxide. And then the negative voltage at the substrate terminal repels the minority electrons upward towards the oxide interface. This voltage repels the electrons, means minority carriers, upwards, okay. Once the gate voltage reaches a certain threshold, enough electrons accumulate at the surface to form a thin conductive n-type layer that allows to flow of current between the source and drain. And there is no current flow through the gate into the substrate because silicon dioxide layer act as a insulator. Only electric field is established here. So it is saying that gate to substrate, across these terminals there is no current flow because of silicon dioxide, and there is only current flow between source and drain, okay, because now the channel is created due to sufficient number of accumulation of electrons at this area, okay, just beneath the silicon dioxide, okay. Then we will see the working of D MOSFET. D MOSFET is a, so before understanding the D MOSFET, we have to understand formation of depletion regions. So the depletion region separating the N plus regions forms the P substrate. The depletion region separating the N plus regions from the P substrate forms due to the fundamental physics of PN junctions. So here is the depletion region, okay. It is separating the two N plus region from P substrate, okay. As we all know, D MOSFET always contains a pre-existing channel. It is observed here. So it is normally on switch, okay, and MOSFET is a normally off switch, okay. And then we will have a diffusion. So in the regions where N plus material rich in electrons touches the P substrate rich in holes, a concentration gradient increases. Means electrons naturally diffuses from N plus region into the P substrate, and holes diffuses from the P substrate into the N plus regions. Okay. So how the depletion region is forming, I am explaining that. So electrons of the n plus region is diffusing into the p type material, and uh, here also same. And p type material, p type substrates, holes are diffusing into the n plus region due to diffusion process. Okay, because it is a tendency when a p and n junction meets. Okay, it is a tendency to flow the electrons of n plus region into the p substrate, and holes of p type substrate into the n plus region. There near the junction interfaces, these diffusing electrons and holes meets and recombine, neutralizing each other. And as the mobile carriers, charge carriers, disappear through recombination, they leave behind uncovered immobile ions that are negative acceptors in the p-type material and positive donors in the n-type material. So we already know n-type material contains holes and negative acceptors, and n-type material contains uh, free electrons and positive donors. So these free charges and holes are combining each other and leaving the immobile ions that are negative acceptors and positive donor ions. So which forms the depletion region. Where it is leaving means positive ions means negative donor ions. So here positive ions means positive donor ions, which is left in the inside, and positive donor ions are left in the p side. Okay, why they are left in the particular sides means because positive donors ions are present in n-type material, and negative acceptor ions are present in p-type material. So that's why they are left in respective sides. Okay, these layers of immobile charged ions create an internal electric field that opposes further diffusion. Okay, and the both p-n junctions are reverse biased. This area now depleted of mobile charge carriers, electrons and holes. In this depletion region, is the depletion region. Okay, the depletion layer exists around the channel also, because the entire end region, which includes both n plus region and physical channel connecting them, as I have showed the pre-existing channel. Okay, is in direct contact with the p-type substrate. Okay, because this contact area forms a continuous p-n junction along the entire length of the device, a depletion region naturally develops along that whole boundary. So here p-n junction is forming around all the area. So that's why depletion region is forming around this channel. Okay, channel also. As long as the channel is sitting against the p substrate, the boundary will always act as a junction and maintain a depletion layer. And then function of depletion region. So when we apply negative voltage to the metal gate, it pushes electrons away from the silicon dioxide. So here we are applying, so this diagram indicates the positive voltage. If we convert this, here we write the negative, here we write positive. Then if we apply a negative voltage to the gate, then it repels the electrons of this silicon dioxide, which is indicated by thick line. So deeper into the substrate, and whole electron recombination occurs. It leaves behind a region devoid of free charge carriers. So electrons repelled into the p substrate. So here the electron hole recombination occurs, and the area developed between this silicon and silicon dioxide and channel is a depletion region. Okay, which is devoid of charge carriers, electrons. Okay, and then so this depletion region grows as negative voltage increases from the top. Okay, near the insulator downward into the channel. This is the depletion layer between silicon dioxide and channel is increasing towards the channel. The combination of electrons and holes in the channel depletes the n channel of free charge carriers, increasing the resistance and decreasing the channel size, and hence current is low between source and drain. When we apply a positive voltage, a gate acts like a magnet for negative charge carriers. It attracts minority carriers electrons from the p-type substrate. So when we are applying positive voltage, so positive voltage is applied to the gate, then it attracts the electrons of the b substrate, and then pulls more electrons into pre-existing n channel. Okay, and function of depletion region. It repels holes in the p-type substrate further away from the silicon dioxide interface. The depletion layer repels the holes in the p-type substrate further away from the silicon dioxide interface. So here is the silicon dioxide interface between the channel and the thick line. Okay, so this depletion layer repels holes in the p-type substrate further away from the silicon dioxide. So this depletion region between this thick line and the n plus region repels the holes further away from the channel into the towards the p substrate. Okay, and instead of towards the bulk of the p-type substrate. Okay, and then instead of region depleted of carriers, we get a flood of additional electrons in the channel. So as it is attracting electrons, so it is we get the flood of electrons. This effectively eliminates any depletion layer that was restricting the channel. So more electrons are packed into the channel between source to drain, so low resistance and increases the channel size, and hence current is high between source and drain. So that's why a MOSFET is act in enhancing mode and depletion mode. First we have seen the depletion mode, and here we have seen the enhancing mode. Okay, and then we will see the differences between JFET and MOSFET. So what are they means a junction field effect transistor is a 3-terminal semiconductor device in which current conduction is by one type of carrier, electrons or holes. 3 terminals are drain, source and gate. So and a metal so here is the diagram. Drain, source and drain, gate, source. Okay, and then it is an n channel JFET and it is a p channel JFET. Okay, and then a metal oxide is also similar. Semiconductor field effect transistor. Metal oxide semiconductor field effect transistor is 3-terminal semiconductor device in which current conduction is by one type of carrier, that is electrons or holes. Three terminals are drain, source and gate. So here is the MOSFET, two types of MOSFET. Here is the E MOSFET and here is the D MOSFET. Here is the gate, source and drain. Gate, source and drain. So next, it is a unipolar device. It is also a unipolar device. Means the current conduction is by one type of charge carrier, that is electrons. And here the current conduction is by electrons in N channel JFET and holes in P channel JFET. And so here are the N channel JFET and P channel JFET. So here the electrons are moving from source to drain. Okay. Here the current conduction is by electrons, and here the in P channel JFET the current conduction is by holes, that is this way. Okay, downside, drain to source, okay, and current is from source to drain. N channel JFET is totally opposite to the P channel JFET. Okay, here the terminals also oppositely connected. Here drain is connected to positive and source is connected to negative. Here the drain is negative connected and source is connected to positive terminal. And here reverse biased in, and here also reverse biased, because N type terminal is connected to P terminal and negative terminal is connected to P type. Okay, then and the current conduction in N channel D MOSFET and N channel E MOSFET is by electrons, and in P channel D MOSFET and P channel E MOSFET is by holes. I'm talking about these two and these two. N channel E MOSFET and N channel D MOSFET, the current conduction is by by electrons. Okay, electrons. Here the conducting channel is created by electrons. Here also, and here the current conduction is by electrons. Okay, this is totally opposite constructed. Okay, to the N channel E MOSFET. Here two P channels are there, here two N channels are there, and voltage is also reversely connected, totally opposite connected. Okay, here also same. So then the current conduction is controlled by means of an electric field between gate electrode and the conducting channel of the device. The current conduction is controlled by means of an electric field between gate electrode and the conducting channel of the device. Here is the gate terminal. Here whole area is the N type bar. Okay. So here it is saying that current conduction is controlled by the gate terminal, electric field between gate terminal and the conducting channel, gate terminal and the conducting channel. Okay, and then why we have seen in the working of JFET. Okay, we have seen in the working of JFET why it is controlled by gate and the N channel. And then it acts like an electric valve where a small voltage applied to a gate terminal, we create an electric field which opens or closes the channel for current to flow. Here is there. Here in the E MOSFET we have to create the N channel. This is the final diagram. In initial diagram this channel will not be exist. Okay, And so we are applying a VGS voltage, and we are controlling the current flowing between source and drain. And here also we are applying a gate to source voltage. Here we are applying gate to substrate voltage. Okay, and here this is in the E MOSFET, and in the D MOSFET we are applying gate to source voltage. Okay, so we can increase or decrease this channel as we have shown in the working. Okay, and then it is of two types: JFET, N channel JFET and P channel JFET, and MOSFET, D MOSFET and E MOSFET, N channel D MOSFET and P channel D MOSFET, N channel E MOSFET and P channel E MOSFET. Okay, and then here the current conduction involves the elements gate, source and drain in JFET. Gate, drain, source. And here the current conduction involves the elements gate, source, drain and P substrate also. Gate, source, drain and P substrate. Gate, source, drain and P substrate. And similarly in the P channels also. And then why the name is JFET means that device contains PN junctions. The boundary where these two materials meet creates the junction. The device contains PN junctions. Here are the PN junctions. PN, PN. Okay. The boundary where these two materials meet creates the junctions. Okay. Here are the junctions. Okay. And these junctions are reverse biased. These junctions are reverse biased. And why it is called FET means this means the current between source and drain is controlled by the voltage applied to the gate. Here we are applying gate voltage as we have seen in the working of JFET. It is controlled by the JFET only, source to drain current. Okay, and then why it is MOSFET? Why it is MOSFET means metal refers to the metal gate terminal. Here metal gate terminal, and the oxide refers to the thin insulating layer of silicon dioxide, SiO2, that separates the gate from semiconductor, P substrate. Okay, here the silicon dioxide, here is the silicon dioxide. Okay, which separate the gate and P substrate, Okay, and then semiconductor refers to the base material or P substrate. Here is the P substrate. Okay, here is the P substrate. In P channels it is N substrate and N substrate. Okay, and then FET means same reason. Field effect transistor means this means the current between source and drain is controlled by the voltage applied to the gate. Here we are applying voltage in these four diagrams also. Here we are applying voltage and we are controlling the source to drain current. And then construction is different from MOSFET, and construction is same for two types of MOSFET and different from JFET. So the construction is here. A JFET consists of a P-type or a N-type silicon bar, means conducting channel. One second. Here is the construction. It consists of P-type or N-type silicon bar conducting channel containing two PN junctions at the sides. This is the bar. The box you are seeing, this is the bar, silicon bar. It is of N-type or P-type. In the N-channel JFET, it is of N-type, and in the P-channel JFET, it is of P-type. Then, and it is also called conducting channel. And two PN junctions are there, PN junction and PN junctions. And it is also repeating the same meaning. And the two PN junctions are as diodes connected internally, and a common terminal gate is taken out. So internally these two PN junctions are connected and gate is taken out, and source and drain are taken from the bar here. Okay. And then JFET polarities. In JFET polarities, uh, in always the voltage from gate to source should be reverse bias, so that it has high input impedance. And this is the normal way of JFET connection. And source and drain can be interchangeable, means a source can be used as a drain and drain can be used as a source. And drain terminal is so biased with respect to source such that the current flows from drain to source. Okay. And in every JFET the ID is equals to IS. And then we will see the construction of D MOSFET and E MOSFET. Here is the gate. The gate is not directly connected to the substrate. Here the gate here gate is not directly connected to this substrate here also. Okay, because in between silicon dioxide is there, and the width is 1000 angstrom. There is no channel. It is indicated by dotted lines. In case of E MOSFET, this is the representation in the circuit. Okay, there is no channel, so it is indicated by dotted lines, and arrow mark indicates the current flow. For N channel it is inwards, and for P channel it is outwards. And in case of D MOSFET, the circuit representation is like this. Here the channel is indicated by dark line. Well, means the channel is already existing. Okay. And drains, gate, source, inward and output, or inward and outward directions, P channel and N channel. Okay. Then so here two heavily doped N plus regions are placed in lightly doped P-type silicon substrate. One N plus region is source and other is drain. They are separated by 1 millimeter. Here are the two N plus regions built in the substrate here also. Okay. In case of P substrate, here the P-type materials are welded into the N substrate. Okay. In this case also same. Okay. And then one N plus region is called source and other is drain. And silicon dioxide is an insulating layer of width 1000 angstrom and also called gate oxide, conducting two plates. Considering two plates, one plate is a metal contact of gate and other is substrate. Between them a silicon dioxide is placed and act as a dielectric. This combination is called parallel plate capacitor. So here we can see the gate, silicon dioxide and substrate. So it forms a parallel plate capacitor structure. And here the gate is act as a positive plate and substrate act as a negative plate, and silicon dioxide acts as a dielectric. Here gate, silicon dioxide and the P substrate. Gate, silicon dioxide, and above the channel there is a P substrate. Okay. And then where the silicon dioxide prevents current from flowing directly from the gate to the N channel substrate, allowing electric field to build up instead. And then the current conduction is by gate to source voltage, The current conduction is by gate to source voltage in D MOSFET, and in E MOSFET is by gate to substrate voltage, as I have said earlier. Then gives high input impedance and gives high input impedance. So why they are giving high input impedance means, so here is there. Input impedance means easy total opposition to the electric current flow, resistance plus reactance offered by a circuit in its input terminals, measured in ohms. Zn is equals to Vn by In, input voltage by input current. How the reverse bias gate voltage leads to high input impedance in JFET, and in reverse bias operation the gate is made negative related to the source. VGS is equals to 0, and this reverse bias voltage creates an electric field that acts in the same direction as the field due to depletion layer, which is in between the gate and channel. So the depletion layer expands. The depletion layer acts as a very high quantity insulator between the gate and channel. That's why the input impedance is so high. So very few carriers can cross it, leading to negligible gate current Ig. We know Zn is equals to Vgs by Ig. Since Ig is extremely small, Zn becomes very large. If we neglect Ig, then also VGS is negative. So how the Zn becomes maximum means we measure the VGS in terms of magnitude. So Zn is maximum. And in the MOSFET and E MOSFET, why the input impedance is very high? Because the silicon dioxide layer is an insulator. It prevents electrons from moving physically from the gate into the substrate, leading to very high input impedance. And in the D MOSFET, when we apply a negative voltage to the metal gate, it pushes an electron away from the silicon dioxide deeper into the P substrate. Electron hole combination occur. It leaves behind a region devoid of free charges. This is a depletion region. This depletion region grows as negative voltage increases from the top downward into the channel. And then gate is made up of p-type material in the JFET, and the gate is made up of metal in both D MOSFET and E MOSFET. And then depletion region formation increases due to the increase of gate source voltage. Reverse biasing, okay, as we have seen in the working in the JFET, okay. And depletion layer increases in the E MOSFET near the drain because VDS increases due to the drain is of n-type material and p-type is of p substrate is of p-type material. So due to diffusion, the electrons of n-type material diffuse over p-type material, and holes of p-type material diffuses over n-type material, leaving behind negative acceptor ions and positive donor ions, forming a depletion layer. In case of high VDS, the electron and hole diffusion is more fast. So depletion region near Dn plus region increases. In D MOSFET, the depletion region increases due to negative voltage to the metal gate, as we have seen in the working of D MOSFET, okay. And then here is the low noise application, JFET, and it is the high noise application, because a device which has minimum amount of internal electrical noise is called low noise application. JFET is a low noise application because they are majority charge carrier devices that operate without the high current PN junction found in BJTs. Reason: unlike bipolar junction transistors, BJTs which require a forward bias base current, JFET uses a reverse bias PN junction for the gate. This leads to the extremely low input current, which eliminates significant short noise, the dominant noise in the BJT. JFET conducts current through the bulk semiconductor material, a channel, rather than along a surface interface, or rather than a oxide interface like a MOSFET. or forward bias junctions like BJTs. This reduces flicker noise. Flicker noise means electrical noise in circuits where the noise increases at low frequencies and decreases at as frequency increases. And oxide trap means in MOSFETs have a conductive channel right under a gate oxide layer silicon dioxide. This interface contains some defects, traps, electrons or holes passing through this channel get trapped and released by these defects, causing fluctuations in the carrier number and mobility. These trapped charges randomly turn portions of the channel on or off, creating flicker noise. So that's why I have stated these two lines. And then identical parameters as MOSFET. Identical parameters as MOSFETs. So parameters of JFET and MOSFET are same. Here are the parameters. Transconductance GFS. Here is the change in the drain current to the change in the gate to source voltage. And amplification factor is the change in the drain to source voltage to the change in the gate to source voltage. And drain resistance RD is equals to change in the drain to source voltage by drain current, change in the drain current. So that's it for today's class. If you have any doubts, ask me in the comment section. And thank you. I will see you in the next class. And if you feel this video is helpful, then like, subscribe and share and comment also. And bye. Thank you. Bye.